Welcome everybody to the 9th webinar of the online edition of the Protelec Electrostatic Conference. Today we will have one flash talk and one full presentation. The flash talk will be from Manuel Ruíz and the full presentation will be from Anna Damjanovic. Manuel Ruíz is a PhD student from the Polytechnic of Milan, and he will be talking about the electrostatic modeling of the interaction of nickel-iron hydrogenases with graphite electrodes. I thank everybody for being here. I give the podium to Manuel.
Okay. Well, first, thank you to Walter for this opportunity to present what I am doing in my PhD. And first, let's see. Okay. Can you see my screen?
Yes.
Perfect. And yes, I want to start. As Walter said, I am doing my PhD in Materials Engineering Polytechnic of Milano, and my thesis advisor is the Professor Guido Raus. The general aim of my project is to understand how hydrogenases interact with the surface of the electrodes. This because at the end, what I really want to do is to find a way to produce hydrogen. And in my case, I am very interested in these enzymes because these enzymes can catalyze the redox reaction of hydrogen. So basically, these enzymes can bond two protons with two electrons, and then we can generate a molecule of hydrogen. The reverse path can be done, so we can take two molecular hydrogen, then we can break it in two protons and two electrons. For the people that is very interested in instead of hydrogen production, more in the generation of the electricity, the reverse pathway is very interesting for that. But the interesting part is that this enzyme can do the both things. In my case, for what I'm interested in hydrogen or why it's important in hydrogen is because hydrogen at the end, for me, going to be the replacement of the actual use of the fossil fuels. For example, with hydrogen, we can give energy to small objects, for example, cars, medium-sized objects, for example, transportation. There are some submarines that works with hydrogen, or even we can use it to empower, to give energy to our full cities. However, the problem that we have in this moment with hydrogen first is that it's relatively expensive to produce. And the second, if we want to use hydrogen in fossil fuel and fuel cells, the problem is that the elements that are using in the electrodes for fuel cells are relatively expensive. For example, most of them they are using platinum. So for that reason, a lot of people is trying to find a way to incorporate the different ways of produce hydrogen or use different materials for the fuel cells. In my case, to resolve this problem, well, I am trying to get the inspiration from the nature. And the idea is that the problem of how to generate hydrogen has been resolved by the nature many years, many millions of years ago. We have a lot of organisms that really can produce hydrogen, in general, bacteria. And the approach that I am trying to follow in my research is to copy the models that already exist in the nature. So in the way that if we can copy the model of the hydrogenases, we can design electrochemical devices, something made for humans, and then produce hydrogen, something artificial. Because, well, this is more like a dream because it's going to take a lot of years of research. In my case, I am more modest. I am trying to follow in the idea of try to resolve the small problems first before to dream in big. And in this moment, the specific goal that I have for my project is to calculate the total energy of the electrostatic interaction between my enzyme, and this guy in this moment is the hydrogenase 1E3D, and the surface on one graphite electrode. This is important because first we need to see if we can attach this protein to the surface of the electrode. And then after that, we need to see if really the orientation of the protein once that is attached to the surface of the electrode is the correct one. This is important because, well, this enzyme is a medium-sized enzyme. It's more or less 89 kilodaltons, but it's composed by two proteic chains. Basically it's an heterodimer. So we have a big subunit and a small subunit. In the small subunit, for research that other people have done, we have, they have discovered that there are some iron sulfur clusters that they works more like a wire to transport the electrons from the exterior of the protein, and they transport the electrons to the interior of the protein, to my enzyme, to the catalytic center, where really happen the redox reaction when we produce the hydrogen. And basically, in the research of that people, they have discovered that the orientation is very important at the moment that we place the protein in the surface of the electrode. So in my case, because I don't, well, at this moment I am not planning to do experiments in the laboratory. I am trying to do simulations in computers. For that purpose, I am using the software of PyGB. That is a software that solves the linearized Poisson-Boltzmann equation and help me to calculate the electrostatic interaction between two bodies. In my case, I am calculating the interaction between the protein and the surface of the electrode. Basically, PEGB helped me to calculate the solvation energy, the surface energy, and the column energy. The addition of these all energies, at least for my experiments, I want to consider like the total energy of the interaction between the surface and my protein. And after that, the idea is, okay, once that I have the total energy of the interaction, I want to calculate the probability of occurrence of certain orientations using the Boltzmann distribution. Basically, with PICB, I need to generate the structure of the hydrogenases. I need to generate the structure of the electrode. I need to assign the charge for the hydrogenases. I need to assign the charge for the electrode. And then I need some files that correspond to the settings that I need to input to PICB to the calculations. For the experimental design, what I am planning to do is, okay, I have a protein, then I have the surface of the electrode. What I want to do is to take the protein, put it in the surface of the electrode, and then rotate it. So I'm going to rotate it first from 0 to 180 in the tilt angle, and then I'm going to rotate it in the rotational angle from 0 to 360. Also, for the experimental design that in this moment I am planning to do, I am trying to test different potentials from 0.05, 0, minus 0.05 volts. And the distance in this moment for the calculations that I am doing between the surface of the electrode and the surface of the protein is about 3 angstroms. Also, I am interested in test different pHs. The range of the pHs is interesting because from the studies that the people has done in the laboratory, they have discovered that more or less this is the range where you really can produce hydrogen. Also, because my protein is medium sized, the dimensions that I select for these simulations for the electrode is more or less like a plate, it's a brick, and the dimensions is 250 times 250 times 10 angstroms. In this moment, for the time, I just going to present 2 cases of the preliminary results that I have got with these simulations. And the first results that I'm going to present is what happened when I put my protein under a pH of 7. This plot is more or less every small square represents one calculation, and the color represents the energy. So deeper the color, lowers the energy, and for that we can see the different orientations with his energy associated. So for my calculations, at least at this pH, the position with the tilt angle 90 and the rotation angle 340 was the position with the lowest energy. With this information of the energies, after that I calculate the probabilities. Obviously, because it's the position with the lowest energy going to be the position with the highest probability of happening, of course. And just for curiosity, if we want to examine it, how looks this position, we can see it in this representation. Basically, once that we place the protein in the surface of the electrode and we apply this condition and then we run the simulation, we see this configuration. For this pH, the interesting part is that at least the iron sulfur clusters that are very important for the transfer of the electron, they are in a position horizontal with respect with the surface of the electrode. The next step was, what happened when I change the conditions? In this case, what happens if I change the pH to 8? In this case, the orientation of the orientation with the lowest energy changes, obviously. And in this case, the orientation is when the protein is in the tilt angle 130 and the rotational angle 257. So this orientation has the lowest energy, and for that reason, the highest probability. If I want, in this occasion, explore what happened with my protein under this situation, I can see that just changing the pH, I can change the orientation of the protein. And this, at least this orientation is more, or at least I want to believe it, is more favorable to the transfer of the electrons from the surface of the electrode to the inside of the catalytic center. Because at the end, this part that corresponds to the iron sulfur cluster is very close to the surface of the electrode. So I want to believe that this orientation is going to favor the production of hydrogen. And well, an image looks very nice, but the problem is that we need to quantify this stuff. So the next step we are planning at this moment is calculate the current of the certain orientations, based in the idea that the transfer of the electrons decrease exponentially with respect to the distance between 2 points inside of the protein. With that information, besides that we already know the probabilities of determinant of the orientation, we have the two informations. So the next step is combine these two informations to obtain the total current. The problem is, if you see here down, we can imagine that I have the plate, and on the plate I'm going to have a lot of proteins. Every protein going to fall in the different positions. Some positions are going to be favorable to produce hydrogen, another is going to be very extreme, another is going to, it's something very random. But then if I consider that I know the probability and I know the current, I can calculate the total current for all the orientations. So with that information, I create this plot, and more or less has some sense with the previous image that I present in the previous slides. So here you can see the total current for at pH 7 and the total current for the pH 8. We can see that there is a difference, and the difference in this, there is a gap between the 2 points. And the difference between the 2 points is, in this moment, I believe, is because we have the right orientation. So the distance between the iron sulfur cluster, the external iron sulfur cluster to the surface of the electrode is shorter at pH 8. And for that reason, I have a higher value of the total current. Just to summarize the preliminary results that I have in this moment is that, okay, if for the future I want to develop my device to produce hydrogen based in a biomimetic approach, First, we need to control the orientation of the hydrogenases on the surface of the electrode. Also, what I see with these preliminary results is that the pH has an important role in placing the orientation of the protein in the surface of the electrode. And at least for the conditions that I am testing in this moment, pH 8 favors the correct orientation of my enzyme in the surface of the electrode. Another result that this take my attention, but I need to be careful about this, is that at least for the plots that I am getting until the moment, very few positions have the higher the probability of happen. For me, this is something that I have some ideas, but I am still not sure why it's happening. And another thing that I am watching from the results that I am getting is that the electrostatic potential that I am plotting in the surface of the protein, when I make the representation, suggests me the natural configuration of the protein inside of the bacteria. Because in general, these proteins likes to be together with another proteins. So the most probably when they are attached to another protein, probably if I remove that protein and then I begin to make the simulations, that part of the protein going to be more favorable to be attached to the surface of the electrode, because in nature inside of the bacteria was attached to another protein, to another hydrogenases. And yes, with this I finish my presentation. I just want to give thanks first to my sponsor, that is CONACYT, is Consejo Nacional de Ciencia y Tecnología from Mexico, and the people that is working in our department and the group of materials modeling. And also I would like to say thank you to Guido Raus, because he's my professor and always is trying to help me in all the doubts that I have when I am trying to resolve this problem. If you want to write me, or if you have suggestions or you have better ideas of how to resolve the problem, here is my email. And yeah, thank you for your time.
Okay, thank you, Manuel. Are there any questions?
I have a question.
Yeah, Alexei,
Yes.
go ahead.
So thank you for the talk. So a quick question: when you calculate, I may have missed it, when you calculate the pKs of the protein, do you take into account its coupling to the surface?
Yeah, sorry, I can't listen you very well.
So
Sorry.
when you calculate pKs of the residues in the protein, do you take into account the surface? So you do, in other words,
No. For this moment, what I am doing is I calculate the solution and where is the protein, and then I calculate the pKa, and then after that, once that I create the PQR, I submit it in the similar conditions for PICB to run the simulation.
my suggestion is to take a look whether the coupling may have an effect, especially since you're discovering that the orientation, so the energy is pretty sensitive to orientation. And so what I'm coming from is you have graphite, right? The surface is graphite, right?
Yes.
Right. So it's a, it's a conductor, and you can have strong image charges. So I think what you could possibly do quickly is a simple calculation whether the protonation state of your enzyme depends on whether the surface is there or not. So full coupling may be complicated, but you can, couple of orientations which you observe, you can do sort of a single calculation and see whether the dependence is there or not. And that would at least, do some cell consistency check. That's it for me.
Okay. Are there any other comments or questions? I actually have one. So you said that the protein is in the functional state is attached to another protein. Can you tell us a little bit more about this? I cannot hear you.
Yes.
Oh, okay.
No, really happened, and okay, I can move. But well, I was reading the article of where my protein was submitted to the PDB data bank, and then the same guy that submit the structure, they say, okay, my protein can be normally, basically, they are.
We missed. Sorry, the mic should stop working at some point. At least for me.
No, probably yes,
You are
my
back.
microphone.
You are back.
I need to check the battery. Yeah, no, very fast. Yes, it's as I tell you. Can you hear me?
Now.
Yes.
Yes. Now
Okay.
I can.
Yeah, I changed the microphone. No, the most I was telling this the guy that submit the structure of the PDB to the PDB data bank. He in the same article they say this protein is associated with another proteins. For example, where is the iron sulfur cluster is my hydrogenase is attached to a cytochrome C3. And after that, the same guy suggests probably, and the other side, because one of my figures present my protein in a horizontal position, and he said the most probably is that this protein is associated with another protein in this orientation. And after that, I began to read another articles with another hydrogenases in a different organisms, and yes, it's true. Sometimes these enzymes are they create some structures to make more efficient the production of hydrogen.
In that case, I would suggest that you take into account possible sterical effect of the dimers or the complexes that may form that might have some relevance in addition to electrostatics to induce the orientation of the protein with respect to the surface. Okay, any other question?
So I have a short question. I can't raise my hand, sorry.
Okay. Christopher, yes.
Yeah. Yes, hi. I worked a lot in that code, so I'm very, very happy someone is using it. So
yeah, I'm happy to know you.
So just asking a quick question. So you tried different potential surface potentials on the graphite, right?
Yeah.
What physically, what did you want to represent there? I mean, what took you to those numbers, and how sensitive was the orientation to that? I had tried surface charges, but I never really. The code is can do the surface potentials, but I never tried it myself. So I'm curious.
Yeah, for me in this moment, what I am considering is because in the code we can define if you are using a Newman surface or the Dirichlet surface. For me in the code, when I am putting the settings, I am declaring that the surface is a Dirichlet surface, and then I apply directly the potential.
Yeah, how did you decide those numbers as potential? Those values for potential. What did you? How did you get to those numbers? I mean, what do they represent physically?
How do you decide the potential of the electron? Yeah. I got it correctly.
How I decided? The first idea that I had was to use the potentials that the people are using in the laboratories to really produce the hydrogen. But then I discovered that the potential are very high. So in this moment, my selection was to select the potentials that I really that really can be modeled using the linearized model of Poisson-Ball maps. Is my criterion at this moment.
Right. Yeah, that was actually exactly where I was going. If you check
Yeah.
for the linearized approximation.
Yeah, because the second option was to use the full equation is the correct way, but yes, I have some limitations in that aspect.
Yeah, of course. No, thank you. Thank you for the presentation also.
No, thank you for hi. It's interesting to know the people that wrote the code that you are using.
I appreciate it.
Okay. Okay. Anybody else has questions? Okay, then I would like to thank again Manuel